All right, so last time we discussed the one-dimensional constant acceleration motion. The theory we use for one-dimensional constant acceleration motion is the kinematic equations, right? We call them kinematic equations. And then we also discussed the real constant acceleration motion in real life, that's free fall, okay? So free fall is any object falling only under gravity, and then it has been verified by many experiments that anything in free fall on the Earth, okay, the change of the rate of the change in velocity is always a constant, and it has been measured to be 9.8, okay. So that's a very famous physics constant, little g of free fall acceleration, we call it, right? 9.8 meters per second squared. So we usually use this symbol little g to represent this constant, okay? So we discussed free fall last time. Now we're going to use this kinematic equations to solve some problems on free fall, okay? So that's what we're going to do now. So this is still the theory for any constant acceleration motion, right? So we can just go ahead and use this theory in free fall. But free fall, it's in vertical direction, right? So we usually call vertical direction y, okay? That's just a convention people use. So usually people do, okay, is that let's just replace all the x's with y's. So I just get the equations in y direction. But there's nothing wrong if just you still use these equations. You just call, you know, vertical direction x, if you like, right? Okay? So all you need to do is just replace all the x's with y. But you don't get like a new theory, right? This is not going to be a new theory. It's still the same theory. We just use them in different equations, different directions. And then people usually call vertical direction y, horizontal direction x, okay? So that's what people usually do when they work in the vertical direction, okay? They're just going to call everything now in y direction. All right, so now, again, as I said, you should be careful when you work with velocity, accelerations, and also forces we're going to discuss in a little bit. They are vectors. They have directions, right? So when you set up a coordinate system, right, like we just saw the problem with the car moving, right? You may have like positive or negative numbers for the acceleration or even velocity and forces we're going to discuss later. That's just telling you the direction, okay? Because once you set up a coordinate system, how do you distinguish in horizontal direction, left and right? We use signs. If you call right positive, then left must be negative, okay? And in y direction, we usually, when we draw a coordinate system, right, I think 99% of people, when they draw a coordinate system, they will draw it this way. Right. So if you assume, when you draw this, you're also assuming up is positive for y direction. So anything down in y direction, you should call them negative, okay? That's how you distinguish them in equations, because you don't write words in these equations, right? Okay, now I get like this number down. I write down 5 meters per second down. No, you can't even plug numbers in, right? How do you plug 5 meters per second down in an equation? Then you do math. You can't, okay? So we're just going to use signs, right? So if we assume up is positive in y direction, anything down in y direction, we're going to call it negative. And free fall is very special, right? If I have a problem in free fall, something is moving in free fall, the acceleration, I already know that, right? You don't need to a problem to tell you, okay, the acceleration is 9.8 meters per second, direction is down. You already know that, okay? That means when you plug this number in, when you plug AY in free fall, you should plug in negative 9.8. Okay, you don't plug in positive 9.8. If you plug in positive 9.8, you're making a mistake. You're assuming this object is moving with the acceleration up 9.8, which is not the case, right, on the Earth. Okay? Or if you want to use symbols, sometimes we're going to see, if I just want to use symbols to draw a general conclusion, like find an expression, okay, I'm just going to use negative g. Because g is equal to 9.8. G is the symbol for 9.8. It's pretty much like pi is the symbol for 3.1415926, etc. Okay? So either way, right? If I want to calculate the area of a circle, and I have the radius, right? I would do this times the radius squared, and then give you a number. If I don't have the radius, I want to give you a expression, I would just say it's going to be pi r squared. Okay? So either way, right? If you want to give me an expression or number, okay? So when we plug the acceleration in for a free fall, okay, only in free fall, right? Because in y direction, something can be moving up with an acceleration if there's an external force on it. We're going to see examples like that. But if something is only in free fall, the acceleration is always down. Magnitude is always 9.8. Okay, so these are the accelerations you plug in. That's how you distinguish up and down in y direction. Okay. So okay, so that's before we solve any problem with numbers, I want you to take a look at these two conceptual questions on slide 13 and 14. Okay, so let's take a look at the question on 13. Okay, you drop a coin at the top of Empire State Building. Okay, please don't do this experiment. As it falls, how does the speed change? How does the acceleration change? Okay, if we neglect air resistance. So that's just free fall. Something in free fall. If something is in free fall, how does the speed change? How does the acceleration change? Okay, if you understand the free fall we talked about last time, you should find the right answer. Okay, when you drop anything, right, when it's falling, the speed does increase, right? It's obvious, right? You can do the experiment, right? If you drop something at a higher location, the impact is stronger. Of course, that's because the speed gets larger, right? So when it's falling, the speed gets larger and larger. Acceleration, well, that's not that intuitive. You have to do experiments, right? Because you need to measure the speed at every second and then calculate the change in speed divided by change in time and compare these numbers, okay? So that's not intuitive, okay? And that's what I usually say. You don't always use intuition, okay? If you want to study nature, okay? Intuition may guide you to the right answer, but in most cases, it will not, okay? So physicists have done this experiment many times, okay, and they have measured this acceleration in free fall. It's always constant and always 9.8 on the surface of the Earth, okay? All right? So that means the right answer is this, right? Its speed increases, acceleration remains constant, okay? Because it is in free fall, okay? Now take a look at the next conceptual question. Okay, so this is another one to test your understanding of free fall. When you toss a coin straight up, okay, we know that if you throw something up, it's going to move up and it's going to turn around, right? It's going to reach the peak at some point and then turn around and then drop to the ground, okay? Like when you do this, right? So that's okay, that's the motion. But I want to ask you, during all this time, how does the acceleration of this coin change if we neglect the air resistance? If we neglect the air resistance, okay? Think about it, okay? What did we say about this, this motion, okay? If you throw something up after this object has left your hand, okay? It's still free fall. Why? Because only gravity is on it. Even though it's not falling all the way, okay, it's still free fall. It's just free fall with the initial velocity up, okay? If it's free fall, how does the acceleration change? We talked about it. Which one is the right answer? It's going to be always g downward. Okay? So I think this can be a little bit confusing for people. That's why, because it's not intuitive. So our intuition, our mind doesn't really calculate acceleration for us. Okay? When something goes up and then turns around and goes down, right? That's what happens when you throw something up, right? After it has left our hand. Okay? On this part, I think everyone's going to agree, right? Okay, of course the acceleration is going to be 9.8 down when it's falling. What about this part when it's rising? Okay, when it's rising, again, obviously, if you look at it, it's going to get slower and slower, right, on the way up. Okay, so the velocity you draw is going to be something like this. At the top, the velocity becomes 0. So that's how you would draw the velocity, right? Okay? So the acceleration, you see that when it's slowing down, it's decelerating, right? On the way up, it's decelerating. When it's decelerating, the acceleration is in the opposite direction. Okay? So you see that the acceleration, it's always down in this whole trip. Doesn't matter if it's on its way up or on its way down, because only gravity is on it, right, after it has already left our hand. So the magnitude, again, it's not that easy to see, right? Even if you do this experiment, you can't even be sure that the acceleration on this portion, right, when it's falling, is 9.8. Again, you have to trust the experiments. You have to do experiments to measure the experiment, measure the acceleration. So because this is free fall as well, so the acceleration, the magnitude must be 9.8, okay? All right? So in this whole process, it's still free fall. This whole process is free fall, okay? So the acceleration is always little g downward, always 9.8, okay? Right? So that's these two conceptual questions. Now let's take a look at the next question. Now we're going to do some math, okay? And this is actually one way to verify that free fall is a constant acceleration motion, okay? So how do we verify that? So now we're going to draw a general conclusion. So I want you to use the symbol or the symbols in the problem to draw a general conclusion. So what conclusion do I want you to draw? If you drop a coin at a height, a certain height h, right, from the ground, of course it's just going to fall to the ground, right? I want you to find expression for this time it takes for the coin to reach the ground, okay? So again, if it's a constant acceleration motion, I can use this theory, okay? That's why we listed this theory here. Now what I'm going to do is that I'm going to assume something. It's going to fall from a certain height h from the ground. Okay? So you drop something at a certain height h, of course it's going to fall to the ground, it's going to get faster and faster, right? That's our, what we see in real life. But now I want you to find expression for this time, okay? This falling time. Okay, how do I find the falling time? Now I'm going to do some algebra, right? You can't do that intuitively. You have to do math. I would use this equation. This equation is kinematic equation. Okay, so which equation do I use? Well, first of all, which equations have delta t, the time? The first one or the second one? So which one do I use? I don't know. I can't predict. I'm just going to try one. If that one doesn't work, I'm going to try another one. Okay. Let's try the first one, right? The first one, it's easier than the second one, so I would try the first one. If I try with the first one, so first of all, I'm going to rearrange that for sure, right? Okay. And then once I rearrange that, I will get expression for delta t. And then do I have all the numbers or symbols I need in this question, right? The only thing I'm allowed to use is going to be this height. And then, of course, constant little g, right? The free fall acceleration is little g. Then you see that if I rearrange this equation, I would get vyf minus VYI divided by AY. Okay, if I use the symbols, VYI is 0, okay, so that's easy. That's a 0. I don't need any number or symbol because I drop it at a certain height, right? I'm not throwing down. If I'm throwing down, I'm giving it an initial velocity. So this guy's going to be 0, but the final velocity, I don't know it, okay? Some people, they may say, well, okay, it's going to hit the ground. Isn't the final velocity 0? Well, that's another process you should be careful. There are two processes here. When this guy is falling, free fall, free fall, free fall, right before it hits the ground, that's still free fall. But when it hits the ground, that's a different process. That's a collision, right? It's very short. So this process is going to be very, very short, very quick process, but that's a collision. That's not free fall anymore, okay? So that's a very short second process right after the free fall, okay? So actually what you need, if you want to use the theory for free fall, you're going to only consider the first process. So the whole process between the point the coin is dropped to the point where this coin, right before this coin hits the ground. That's the whole process, okay? So you're going to need the velocity of this guy right before it hits the ground, okay? So you can't use 0, right? We know that right before it hits the ground, it definitely has a value, right? And then it's going to carry that value, that velocity, and hit the ground. That's a second process. That's the collision, okay? We're not interested in that collision here. We just want to find this fall time, okay? So we don't have this VYF. We don't have a symbol for that. We don't have a number for that. So the first equation looks like it's not going to work. But don't worry, we have another equation that has t, right? So let's try the second equation. If the second equation doesn't work, okay, I may need to find a different way to do that. I may need to combine some equations to find the time. So let's try the second equation. So I would have this, YF equals YI plus VYI delta t plus 1/2 AY delta t squared. Now let's see. Okay, looks like I'm solving a quadratic equation. It's a little bit harder than the first one, but the initial velocity is 0, right? So you will get YF equals YI plus 0 plus 1/2 AY delta t squared. Now let's see, do I have all the information I need? What is YF? YF is the final height, the height of the final position. That's the ground. Of course, you can assume it's 0, right? We usually assume ground is 0, okay? If you assume ground is 0, what is the initial height? Oh, that's just going to be this h, because you tell me you're going to drop this coin at a height h, okay? So this is 0. Now, what is the acceleration in y direction? Okay, negative 9.8 or negative g I plug in if I still use this coordinate system, okay? If I still use this coordinate system, now I want a general expression, so I'm not going to plug in negative 9.8, I'm going to plug in negative g. Why? Because I assume up is down, okay? Oh, I'm sorry, I assume up is positive. The acceleration is down with a value I call little g. So I'm just going to plug in the symbol, okay? Now you see that I do have all the symbols I need, and it's very easy. I only need this h and little g, so I can rearrange this equation and find expression for this delta t, okay? All right, so now you can finish the algebra and find expression for the delta t. All right, so let's see. If you rearrange this equation, what do you get? You will get a very nice equation, this. Okay, delta t equals square root 2 times h divided by little g. Now you can say, okay, if I want to really find a falling time for a coin dropped from like 2 meters, you plug this in, you plug 9.8 in. Now you can use the value, right? Remember, little g means 9.8, okay? Whenever you see little g, you can just replace it with 9.8 if you want to find a number. It's pretty much like when you see pi. If I only need the expression, I leave pi there. But if I want to calculate the value, I'm just going to replace pi with the number it represents, 3.1415926. Okay? All right, so that's the general conclusion, and that's the conclusion I want you to draw, so that you see that if I drop anything, right? So it doesn't matter what you drop, but you don't drop a feather on Earth. If you want to use a feather, you should go to the moon. You drop anything at a certain height, you can always use this expression to predict the falling time, right? If free fall is a constant acceleration motion with this 9.8 meters per second squared as the acceleration, right? So that's a way for us to confirm that theory, okay? If you tell me, okay, when I drop anything in free fall, it's gonna be in a constant acceleration motion, which is not that obvious to me, right? I know it's getting faster and faster, but how do I know the rate of the change is a constant, right? Our brain cannot process that for us, okay? Our brain is only going to tell us that it's getting faster and faster, intuitive to us, right? But if you tell me actually the rate of the change in the velocity is a constant, is always 9.8, okay? So how do I do to believe you? I would need to do experiment, okay? That's how we test a theory in physics, okay? If you want me to believe a theory, you need to tell me how to do an experiment to verify the conclusions from your theory, right? This is the conclusion from the free fall theory. If we say free fall is a constant acceleration motion with the acceleration 9.8 meters per second on the Earth, always there, this will be the falling time of anything you drop at any height. Now you go ahead, do an experiment, okay? If you can confirm this, if the time you measure in anything falling in free fall agrees with this prediction, then you will believe my theory, right? And you can repeat this experiment with different things, different heights, right? If you have done that many times, your experiments always agree with the theory, then you will believe the theory, okay? So that's something we will do here. Actually, we can do that. So all you need to do is just drop something and measure the falling time, right? Measuring the falling time is a little bit hard, right? Even if you want to use a stopwatch, there's always some reaction time if you want to click the stopwatch, okay? Start it and stop it, okay? Unless you drop something at a very, very high location, okay? If you drop it at like 1 meter, 2 meters, it's gonna hit the ground less than a second, okay? So it's really hard to do if you want to drop something and with a stopwatch and then you want to click the stopwatch, okay? So we do have a nice thing here in the department, which is called G-ball, okay? So this thing can measure the falling time very easily for us. So how does this thing work? So I'm gonna go to the camera to show you how it works. So there is a timer here, okay? I'm gonna show you. You see the timer, right? So there is also a button here, you see that, okay? So the image may be reversed, left to right, reverse. But there's a button push here. So what this button does is this. You're gonna first push this button. Okay, it's not running, right? And then once you release it, it's gonna start timing. Okay? And then if you drop it there and then it hit anything, the timer is gonna stop. Okay? So you see that now the timer has stopped. Okay, again, it's left and right reversed because this is mirrored. So I don't know how to make this right, but anyway. So that's a nice feature because what we can do is this, right? I'm just gonna drop this guy at a certain height with my finger on this button, right? So I'm gonna push this button, then it knows that I'm ready, and then I'm gonna just release that, right? And once I release that, I release the button, it's gonna start timing, and then this guy starts to fall, right? So it starts timing as soon as this guy starts to fall, and then when it hits the floor, it's gonna stop timing. So this timer is gonna just measure this falling time for us, okay? So that's how we're gonna test this theory. So you can pick a height, right? Say I want to pick a height 1.5 meters. Let's pick a height 1.5 meters. So now I want you to use a calculator and then predict the falling time for me. If I drop this G-ball from 1.5, okay, from the ground, how much time does it take for this G-ball to reach the ground? Okay. All right, so what is the time you got? Okay, if you use this expression, this must be a general conclusion, right? So 2 times 1.5 divided by 9.8, take the square root, don't forget the square root. So the time, our prediction based on the theory we just learned is going to be 0.55 seconds. Okay, so now we're going to do this experiment, okay, and because this is a real experiment, so we should have, we will give it some error range, okay, so like plus minus 10%, something like that. So let's see if we can get any value very close to this, okay, maybe not exactly 0.55, so it should be something very close to this, okay. Now I'm going to go to the front, do the experiment. So I don't know if you can see that I have a 2-meter stick here, okay, and then this 150 marker is here, okay. Can you see this? Yeah, this is 150 marker, okay. So I'm just going to drop this guy, okay. First of all, I'm going to push this button, right, and then I'm going to drop this guy with the bottom at the 150 centimeters, that's 1.5 meters, right? And then once I release that, it's going to start timing, and then once it hits the ground, it's going to stop timing. Okay? So now you see the time I got. Okay, again, it's left and right reverse. It's 0.60, okay, seconds. So it's close, but it has a 10% error, okay, which is actually very good in such an experiment, classroom experiment. And then if you want to make this experiment more accurate, what do? We repeat this experiment many times to take the average, right? So for example, if I repeat it, do I get anything like close to this? I can repeat this experiment, right? So now I'm going to 0 A. So now it's 0, 0. Right? Now I'm going to repeat this experiment one more time, see if I can get something still close to this. So I'm convinced it will be like that. Okay, what is the value I got now? Now this time I got a little bit closer, which is good. 0.58, okay, 0.58. So closer to that. So let's do it one more time, see if I can get, but this is already very good, okay, 0.58, already very, very good, okay. And then let's do it one more time, okay. So that's how you make your experiment result. So now I'm gonna 0 it again, okay, and then drop it at 150. Wow. 0.57, even closer, okay? So you get my idea, right? If you want to really do an experiment to confirm a theory, you don't do it once, right? You're going to repeat it many times. You're going to take the average. You're going to take the average, okay? Then you're going to compare the average value with this prediction. So what we did, very, very close. If you repeat this 10 times, okay, you can take the average, but we can see that it's all very close to 0.55. So that's how I verify this theory. So if I repeat this like 100 times with different heights, okay, and then I always get the experiments agree with these predictions within a very, very small error, okay, then I believe this theory is right. That's how we believe a theory, okay? All right, so at this point, I usually get this question, oh, this looks a nice equation. Do I need to memorize this equation? No, you don't, okay? Remember, I repeated many times, physics is not about memorizing conclusions. How did we get this? We get this using the kinematic equations, right? So the idea of this, if you have a free fall problem, you always use this theory, okay? You always use this theory. You will always get your answer, get the right answer, okay? You just need to pick one of them, or sometimes two of them, okay? Or even three of them. You manipulate them based on the numbers you're given, based on the story you're given, the problem. And then you're gonna do the math carefully, you're gonna find the right answer. Either it's an expression or it's a number, doesn't matter, okay? A lot of people, they have difficulty working with symbols. That's something you need to get used to in physics. If we want to draw a general conclusion, okay, not some numbers, okay, I want just to use these symbols, okay, and manipulate these symbols to get a general conclusion with symbols, so that anytime I want to do something similar, I want to repeat this experiment with different numbers, I can go ahead and use this conclusion, plug numbers in, right? That's what we do when we want to draw a general conclusion, okay? And we don't want to memorize these conclusions, okay? This is an experiment we set up, right? If the problem gives you something similar to this, of course you can plug this in, right? Get the right answer. But what if you get a different story, right? Which is not this experiment, right? Then this doesn't apply. You may draw a different conclusion using these three equations. Do you need to memorize that conclusion as well? Then at the end you will see that, okay, there's so many different types of questions, so many different types of stories in physics. Then you're just going to remember all these conclusions? No, that's not what we are doing in physics, right? What we're doing, we're learning this. If this is the theory for constant acceleration motion, so if you give me any type of constant acceleration motion, right, free fall in y direction or something moving in x direction, I would always use the same theory. I would always start with the same theory, okay? Use the numbers you give me to make predictions to get the answer you need. That's the idea. I don't need to remember some conclusions or shortcuts so that I can just, you know, when I see a similar story, I just plug numbers in and then get the answer. That's not called physics. We're not doing that in physics, okay? We're not memorizing conclusions and shortcuts so that we can just go ahead and plug numbers in and get the answer. No, that's not what we're learning in physics, okay? All right, so now let's take a look at the next question. So the next question, we will get some numbers. So now we're going to do some algebra with some real numbers, okay, in a very specific question. Let's take a look at this question. A student throws a stone from the top of a building with the initial velocity 18 meters per second past it. Okay, so that means it's up, right? The stone is launched 50 meters above the ground, and it just misses the edge of the roof on its way down. Okay, so it's just telling you, okay, it's not going to hit the roof on its way down. It's going to miss the roof. So on all this trip, this stone is in free fall. Nothing is on it except gravity. Okay, so that's what we want to do here. So we want to find a few things in this whole process. So let's see what we want to find first. How long does it take the stone to reach its maximum height? Okay, so let's first draw it out, and then we're going to use the same theory to find things we need. Okay, that's what we're learning in physics. So this is going to be the trajectory of this stone, or anything, right? It's just going to be an object to me. It starts from here, which has 50 meters from the ground. Okay, and then I want to find the, of course I know that when someone throws it, it's gonna move up, okay, get slower and slower, reach the top and turn around and then drop, okay. Now I want to find how long does it take the stone to reach its maximum height. So I'm focusing on this portion, right? So I'm only focusing on this portion on its way up to the top. So if I want to find a time, okay, I'm going to pick one of these equations, okay, because that's the theory I learned for constant acceleration motion. So I will always use this theory for constant acceleration motion. Do you pick the first one or the second one? Because both of them have a time. try one. If that one doesn't work, try the other one. Okay, let's try the first one, because the first one looks easier than the second one, so I would always try this first one first. So if I do that, I would do this, Vyi plus Ay delta t. Now rearrange this equation. If I want to find time, I would get Vyf minus Vyi over Ay. Now let's see if I have all the numbers I need. If I do have them, I'm going to plug them in, right? Ay, as I said, now you're going to plug numbers in. If you still use this coordinate system, the acceleration is down. How do you distinguish down? How do you tell the equation that I'm using acceleration down? I want to plug in an acceleration down. In this equation, you put a negative sign with in front of this number. So you're going to use negative 9.8, right? Now, what is the final initial velocity? Initial velocity is easy, right? The problem already tells us that the student is going to throw this stone with an initial velocity 18 meters, right? Okay? So it has an initial velocity 18 meters per second at this point, if I call this initial. What is the final velocity? Which point do you call final? Okay? So it doesn't have to be always the very end of this motion. You can pick any point as the initial and final in this process to find things you need, right? Now I'm interested in this portion of this part of the trip. I only want to find this time. So that means if I use any of these equations, I need to make sure this is the final point, right? So that I use initial and final, I find the time using these equations, that's going to be the time between this initial and final points. Okay? I'm not going to pick this point or this point as the final, because that's going to help me find this total time, and which is not the question asked in this part, right? So I'm going to pick this as a final point. What is the final velocity at this point? Okay, the problem doesn't say, but think about it. That's the top. If it has reached the top, that means it cannot go any higher. If it cannot go any higher, that means it doesn't have any velocity up at the point, right? It has a velocity up, 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 smaller and smaller, smaller. At this point, the velocity becomes a 0. Then it's going to turn around, then gravity is going to pull it down. So at this point, the velocity is going to be 0, right? So final minus initial divided by the acceleration. Now you see that if you get all the signs right, okay, you will get the time with a right sign, because time cannot be negative, right? If you get a negative time, that's something wrong, okay? All right, so you put all these numbers in. What is the value you got? The value I got is 1.84 seconds. Okay? So this is this part, okay? We used the same theory. We picked the first equation. It worked. Okay, good. That means I don't need to use the second equation. Now, what is the, let's take a look at the second part. Find the maximum height of the stone measured from where it is thrown. Oh, so that means I want to find this height, okay? Measured from where it is thrown, so I only need this distance. I don't need this height, right? The problem says this, very explicitly. I don't want height from the ground. I only need the height from where it is thrown to this point. So I just need this distance, okay? I just need this distance. If I want to find that distance, I'm still only interested in this portion of this process. I can still call this initial and final. I can call this initial and final, okay? So now if I set this is my origin, right? I call this equals 0, okay? So that's a 0 point, and then if I can find YF at this point, that's just gonna be the maximum height measured from where it is thrown, right? So now let's see, which equation has YF? It's got to be one of these equations, always these three equations. That's going to be either the first one or the second one or the third one. So which one do I use? Well, try one, okay? So let's try the second one. I try the second one, okay, initial point I'm assuming is 0. I pick that as my origin. Initial velocity, okay, I do have the value. The time, oh, I just found the time, right? All right, then the third term, 1/2 acceleration plugging acceleration is down. How do you tell the equation that you're plugging an acceleration down? Negative 9.8. You don't plug in positive. Then the equation thinks that, oh, you're using acceleration up. This thing is moving up and it gets faster and faster, which is not the case here. It's moving up but getting slower and slower. It's decelerating. Acceleration is down. All right, so that's how I find this YF, right? Now you can plug numbers in. What is your answer? The answer I got is 16.6 meters. All right, so that's 16.6 meters. So that's this height, right? So this total height is 16.6 meters, okay? From where it is thrown to the maximum height. Now what about the next part? Find the velocity of the stone when it reaches the height from which, returns to the height from which it is thrown. Okay. So I want to find, now I want to, so okay, I know it's going to go up, turn around, and then drop. So it's going to definitely pass the point it was thrown, the initial point, right? So now I want to find this velocity, okay? If I want to find this velocity, okay, so you are, which equation do we use? So now you see that I would say, if this is yi, okay, this is the initial point, I'm not going to use this as my final point, right? Because I'm interested in anything, something at this point, I would call this as my final point. Now I'm going to consider this whole trip, this portion of this trip, okay? So I want to find the the final velocity at that point. So I would use either this equation or that equation, right? So either one. So if I want to use, then you're gonna also pick your initial point, right? Initial point, again, you can pick any point as the initial point. It doesn't have to be always the very beginning of the portion, this process, right? You can pick any point you think is easy to use as the initial point. So in this case, a lot of people, they would say, well, why don't we pick this point as the initial? Okay, so now I'm not going to pick this as the initial because I'm working on a different part. I pick this as the initial. If I pick this as the initial, okay, so let's see. I'm going to use which equation? If I use the first equation, okay, I'm looking for the final velocity. What is the initial velocity at the top I picked? Well, that's going to be 0, right? So if I use this equation for that process, okay, so I'm going to erase things here. I'm going to do it here, okay? So now I'm interested in, now I'm going to label these points, okay? So the problem says, let's call this A, B, C. So now I'm interested in the process from B to C. So of course, B is my initial, C is my final. The initial velocity, it's going to be 0, right? Because that's the point B, that's the very top. I'm looking for final velocity at the bottom. So I'm going to plug in initial velocity plus acceleration, negative 9.8. Okay, that's the acceleration down. What is the time? I don't have the time from this point to this point, okay? But if you can realize that this is just this portion reversed, okay? The time must be the same, okay? This is just like the mirror image of this portion. So the time is going to be 1.84 seconds, okay? So if you plug all these numbers in, you should get 18 meters per second negative sign. Okay, I get a negative number. Okay, did I do anything wrong? Okay, no, you didn't do anything wrong. Because at this point, what is the direction of this velocity? Down. If you still use up as positive, the velocity technically you get, strictly speaking, should be negative because the velocity is down. So you see that the answer is telling you both the magnitude and the direction very precisely. Okay, even if you cannot figure out what the direction of the velocity is here. Okay, I'm stupid. I don't know at this point the velocity is going up and down. The math is going to tell you everything. The math is going to tell you everything you need. okay? You don't even need to figure it out intuitively, okay? It's going to tell you, the math is going to tell you everything, okay? Or if you think, well, I don't really see that, this time is 1.84, okay? The same as this, I don't like that. You can try the third equation to get the V final. So let's try that. If I do this, I would use y initial, which is 0 squared, plus 2ay, negative 9.8. Now I'm still picking these 2 points, but now I'm using the third equation. yf minus yi, okay? yf minus y, remember we set this as 0 height. So in this case, my yf is going to be 0, right? I'm looking for this process from B to C. So if I call this is my 0 height, this is the 0 height. My final height is 0 in this process. What is the initial height? That's the initial height, right? Because that's the height of this B point relative to A. So now the height is going to be the same because it's the same point, right? Okay? If you use this equation, you can also find the final velocity. You're going to take a square root at the end. And when you take a square root, a lot of people, they just pick the positive value, okay? You actually get 2 of them, right? You take the square root of the right-hand side, and you see that all the signs are going to work out. This is a negative number, that's fine. You get a negative number here. You multiply both of them, you get a positive number so that you can take a square root. You get this, you actually should pick the sign negative, right? Because you know the velocity is down here. Okay? So either equation, you get the same answer, all right? Now this is this part. Now the last part, find the velocity of the stone when it is 32 meters above the ground. So which is the point D the problem labels. So it's somewhere here, and this distance is 32 meters, okay? So now I'm going to erase this. I don't think I need this anymore. Okay. So now you want to find the velocity at this point, okay? You want to find the velocity at this point. I would just call this point final. So this is not my final anymore. And is this my initial? Well, I'm not sure. I can pick any point as my initial, right? So I'm going to see which point is easier for me. So if I pick this as the final point, I need to use an initial point, okay? So you can actually pick any point as an initial. You can pick A as an initial, B as an initial, C as an initial, right? Because you already know the velocity here, here, here. So Vyi is not going to be a problem. Doesn't matter which point you pick as an initial. It doesn't have to be always A. It doesn't have to be always the very beginning of the motion. Now let's see. If I want to use the second equation or the first or the second equation, I would need the time, right? So if you pick A as the initial, you need this whole time. But you don't have the time from C to D. Okay, so that's not going to work. If you pick B as the initial, you're going to need this time. But you don't have this time either, because the problem is that you don't have the time from C to D. And of course, if you pick C as the initial, you still don't have the time. So the first and second equation, they can be solved, but that's a little bit hard, okay? So the easiest equation is going to be the third one, okay? If you pick the third one, the third equation, you see that the Vyi is going to be a number we already know, okay? If you pick A, B, C, any of them as your initial point, we already found the number, right? The initial velocity. 2ay. Ay is still free fall, still negative 9.8 I plug in. Yf minus yi. Yf, now you can say that, okay, let's call the ground 0. The ground is 0 height, so the final height is going to be 32 meters, right? You can even change the reference point in different parts, but again, you need to stick with the reference points you pick. If I pick this as y0, so any point I pick as the initial, I should need the distance between the floor, the ground, to that point. So now you see that the yi depends on where I pick, but A, B, C, I already know their height relative to the ground, right? So it doesn't matter which one you pick. you can always use the third equation to find the velocity at point D, because you will have all the numbers on the right. You just put numbers in, take a square root. Okay, so you can pick any of these 3 points, set them as your initial, and then put numbers in, find the final velocity at point D, which has 32 meters above the ground. All right, now you can pause the video, find the point, and then do the algebra. So say, I think a lot of people, they will pick C or B, okay? Because they always think that, oh, because this guy turns around, so I can't use this as a whole process. Yes, you can, because this is free fall. Okay, if it's a free fall, it doesn't matter how many turns it makes, it's still free fall. It's still one acceleration, constant acceleration. I can use the theory. Okay, so let's just pick A as my initial. So I will pick A to D. This is my initial, this is my final. So I'm going to put all the numbers here and see if I can find the right answer. So VYF equals, what is the initial velocity? 18 meters per second. Acceleration, negative 9.8 for this whole process. So it doesn't matter, I'm just going to put negative 9.8. Final velocity, final height, 32 meters, right? Initial height, well, the problem says this has 50 meters from the ground. Now it's going to be 50. You put all the numbers in, you're going to take a square root. Again, when you take a square root, you actually get positive and negative 26 meters per second. And in this case, which number do you pick? You don't always pick positive. A lot of people, they just pick positive, okay? In this case, you actually need to pick negative, because you know that at this point, the velocity is down, right? Okay? And then you can see that if you have used the C or D as the initial point, you get exactly the same number, okay? So you see that physics doesn't depend on the reference point you pick, the initial point you pick, okay? You always get the same answer, and okay? And if something like, in this case, something turns around, but the acceleration is still the same in this whole process, you can consider this has one trip, one process. Go ahead and pick initial and final points, and then go ahead and use this equation. Don't be afraid of picking this one and this one as your initial and final, because it turns around. It's still one process, okay? That's the power of these theories. That's why we learn theories. You don't have to do things intuitively. You just use the theory. You always get the right answer, okay? I'm gonna stop here for this video.